Welcome back to the CIE A-Level Physics Paper 4 question paper from the February-March 2025 series. So before we go into this paper, some resources that we have developed and you will find them immensely helpful. We have already neatly packed them in this grade booster pack. This is available on our Patreon. We will give out the link below in the description. What it contains. This one is definitions and formulae for AS. As you can see, it contains everything. This is just a table for reasonable estimates that can come in MCQs and often in paper 2. All the important key terms and formulae. Then we have important derivations, the ones that are required by the syllabus and often asked in the exam. Then we have frequently examined questions. These are mostly from paper 2, and we're working to include some very frequently examined questions from paper 1 also, but this is still a very good thing. Now, the A2s, since we're going paper 4, these are the resources that we will be using. So definitions and formulae, just like for the AS, all the relevant key terms, all the relevant formulae. Then we have important derivations. We know we get a lot of derivations, capacitor ones, the gravitational ones. We often get them. So these derivations are going to be very helpful for you. Then the most important one, the frequently examined paper 4 questions. So if you notice how we have structured this, on the left side you have the syllabus points that are from the syllabus, the questions corresponding to those, the marking scheme aligned answers, full answers, not just the key points over here. This is just fully grammatically complete sentences, and the years listed on the right side where they are most frequently asked. So if you find that there's some questions don't have years next to them, either we just included them because they were interesting or they were slightly older, but still important questions. So, but there will be some questions, for example, you see over here with a lot of years written over. So that means there's a very good chance that you might see one of those questions. All right, and last but not the least, for the graphs. So graphs are very important in A2 paper 4. So we know we struggle with the field graphs, gravitational field potential, and similarly electric field potential. So we have already included them. It's already very helpful. And for paper 5, it's a planning question checklist. This is based on the syllabus requirements, the marking scheme requirements, and it also includes some worked examples from past paper questions, October number 2024, 5.1, 5.3, and 5.2. So your methodology might slightly be different, but this is just an example of how thorough and detailed you can be. And this is these all 8 files are available in this grade booster pack. Again, we will leave the link in the description. All right, so starting with the paper, let's see. A steel ball is placed on the inside surface of a hollow circular cone. The ball moves in a horizontal circle at constant speed. So we can actually see this horizontal circle. The angle of the side of the cone to the horizontal is 52. There is no friction between the ball and the cone. This means that there is no component of friction that's contributing to the centripetal force. So figure 1.2 shows a cross section through the cone and the steel ball. On figure 1.2, draw labeled arrows to show 2 forces acting on the ball. So since there is no friction, there are only 2 forces. So there is weight and perpendicular force, which is called normal reaction force. You could also call it as normal contact force also, but either way it's the same. Describe how the forces acting on the ball cause its acceleration to be centripetal. Okay, now before we answer this, let's see this over here. So weight is vertically downwards. It has nothing to contribute to uh, centripetal force because centripetal force is directed towards this way. How then we resolve the normal reaction force into these vertical and horizontal components? So the horizontal component of the normal reaction force is contributing to the centripetal force, is equal to the normal centripetal force, and that's exactly what our answer is going to be. So the vertical one is just simply equal to weight, and it's perpendicular to the direction of the circular path, so it's not contributing. But the horizontal component of normal reaction force is equal to the centripetal force. So that's exactly what we just need to write. So the vertical component of normal contact force or normal reaction force is equal to weight but it does not contribute to centripetal force. So it does not, you can say but or so, but does not contribute to centripetal force. However, the horizontal component is equal to the centripetal force towards center of the circle, and they use the word acceleration over here. You can end it with causing centripetal acceleration. That's it. So we needed to describe how the forces are causing the acceleration to be centripetal. So first off, we need to describe that the vertical component of the normal reaction force is, since it is perpendicular to the direction of the circle or the plane of the circle, it is not contributing to the centripetal force. However, the horizontal component of the normal reaction force is indeed doing so. All right, so let's move on. The ball moves in a circle of radius 0.15 meters. Show that the speed of the ball is this. Okay, so first off, we need to get our forces correct. So we have this ball over here. The forces that A is mg, and this is our normal reaction force. You can call it R, you can call it N, whatever you want to call it. And again, as the word suggests, as the word normal means, it's perpendicular to the surface. Now we need to resolve the one of those, either the reaction force or the mg, into uh, into horizontal and vertical. So what we can do there are multiple ways of doing this. So we can say that this component, the vertical component, and the horizontal component of the reaction force. This angle is 52, so therefore this angle that means parallel to the vertical, this would be 38. Therefore, this means that this angle would be 38 this angle would be 52, and therefore this angle would be 38 again. So this means that this is your R sine 52, and this is your R cos 52. So what we have over here, sorry, since we need the centripetal force, R sine 52 is equal to mv squared over R, and the other one, R cos 52, is equal to mg. Now, if we divide both of the sides together, so R sine 52 divided by R cos 52 equals to mv squared over R divided by mg. See what items can be simplified. R and R get cancelled, M and M get cancelled. We're left with sine over cos. That leaves us tan 52 degrees equals to V squared over RG. And we need the V, so V would be RG tan 52 degrees. So this would be 0.15, sorry, 0.15 times by 9.81. Actually, we should write this 0.515, sorry, times by 9.81 times by tan 52. Once we find that, we need to do V. Answer, this is 1.37 to roughly equal to 1.4 meters per second. Okay, so calculate the angular speed omega of the ball. So we know how to figure this out. So omega is equal to V over R, simply because V is equal to R omega. So that would be just simply 1. You can use 1.372, you can use the 1.4 also, divided by 0.15, 0.15. So either way, you're getting this same thing, whatever you want. Okay. So 1.37, sorry, no. 1.372 divided by 0.15, you get 9.147. And the other one, which you do, divided by 0.15, 9.33. Okay, so this is a choice now, whichever one you do. Since we rounded to 1.4, it would be appropriate to use this one better. However, it really does not matter. You can still, if you show you're working with the 1.372, you can use that also. All right. Speed of the ball is increased. Explain why the radius of the circular path of the ball increases. Okay, how do we actually make sense of this? So we, if we go above over here, and we point out something very peculiar over here. So we said that R was actually related to mg, and the R cos 52 was equal to mg. So simple weight, right? And the other component of the R was equal to the centripetal force. We actually brought this over here. We simplified to this. So what we have over here, the relationship that we have is V squared RG tan theta. So this G tan theta is basically constant. So basically what we have is V squared is directly proportional to R. right? So that is not exactly changing. Another relationship which you can see over here is that if you isolate the v squared over r from this, v squared over r is equal to g tan theta, which is the centripetal acceleration. So g and tan theta, they're constant, so acceleration, centripetal acceleration is not changing. So that's what we have over here. So we will say that since acceleration A equals to g tan 52 and remains constant, velocity squared v squared is proportional to radius r. So therefore, if speed increases, radius also increases. That's it. Okay. Question number 2. The magnitude of the gravitational potential on the surface of a planet of radius r is phi. The key word over here is that they're talking about the magnitude of the gravitational potential. The planet can be considered to be an isolated sphere. On figure 2.1, sketch the variation of the gravitational potential with distance x from the center of the planet of the values x between r and 4r. Okay, so just to show you, we do have the graph for that. Yeah, so we go a little bit up. We have the gravitational potential. So yeah, so gravitational potential is this thing. So it's always negative. And the relationship is that phi is inversely proportional to r. The first point entirely negative, and that is proportional to r. That's what is very, very important. So how do we interpret this and how do we write it? So phi is equal to minus gm over r, or you can say that this is minus phi, basically, because they just said phi is the magnitude. So this is the phi could be the gm over r part. Okay. Now, how do we interpret the inverse relationship? So at r, phi would be just r of that, right? This is where we are starting. So at r, we have minus phi. But at 2r, so when you do minus gm over 2r, so basically you are multiplying half with the gm over r. So basically half of minus phi. So, or minus half of phi, basically. So this would come out to be here. Then at, again, 1/3, then 1/4. So we have to figure out where these things are. So this would be 1/4. This would be 1/4. That means half of this. So basically this would be over here. And 1/3 is basically 0.3 basically. So this would actually pass from like this. So notice that this is actually maybe somewhere going like this. So few points that are important. At R it's minus phi, at 2R it's half, at 3R 1/3, and at 4R 1/4. That's it. Um, okay. Then we have, actually you can label this also. So you have 4R minus 1/4 of phi. You could label this one also 3R minus 1/3 of phi. This one is 2R minus half of phi, sorry, and this is R minus phi. You don't need to label it, at least the line should be the correct one. Okay, a satellite is in geostationary orbit above the Earth. At time t is equal to 0, the magnitude of the gravitational potential due to Earth at the location of the satellite is phi. On figure 2.2, sketch the variation of the gravitational potential due to Earth at the location of the satellite for values of t between t is equal to 0 and t is equal to 24. So since this is in the geostationary orbit, that means the radius is not changing. So gravitational potential over here, phi, which is minus gm over r, or like whatever you want to call it, like this way also, the radius remains the same. So the gravitational potential does not change. So the gravitational potential will stay constant. So it starts over here, ends over here. So this is something that is not changing. That's it. Again, since the radius of the path or the orbit is not changing, so the gravitational potential remains same. Okay. The electric potential between two parallel plates is V, as shown in the figure 2.3. The distance between the plates is D. The region between the plates is a vacuum. On figure 2.4, sketch the variation of the electric potential with distance from the positive plate. Okay, so over here you have ground, so this is 0. Sorry, just simple, my bad. Simple 0 volts. And since this is parallel plates, we usually say that this is a uniform electric field. So uniform electric field, that means the potential change is also going to be uniform. So the electric potential will actually grow this way from V to 0. And we have also shown this over here. So let's see, electric fields. Electric fields due to parallel plates. This one. So electric field is uniform, so it's constant. But since electric field is the negative gradient of the potential graph, so it's going to start from V and at 0 between as when the separation ends. So this is exactly what we have over here. So we are starting with V and ending at D. That's it. Sorry, this would be like slightly above. Okay, yeah, that's it. Okay, moving on. Question number 3. Two metal cuboids P and Q are in thermal contact with each other. P and Q are in thermal equilibrium. State what is meant by the term thermal equilibrium. Thermal equilibrium means that there is no more net transfer of heat or thermal energy. So again, let's show you where you can find this over here. So this is the temperature chapter. So yeah, explain what is meant by a statement that two bodies are thermal equilibrium. It means that they are at the same temperature and there is no net flow of heat between them. So we are going to state that it means that they are at the same temperature and there is, sorry, no net transfer of heat. You can say heat or you can say thermal energy. Either way, it's fine. Data for P and Q are given in table 3.1. P and Q are initially both at the same temperature. That means thermal equilibrium already because they already told us that P and Q are in thermal equilibrium. Okay, so P is supplied with 24 kilojoules of thermal energy. After some time, P and Q are once again both at the same temperature as each other. P and Q are perfectly insulated from surroundings. That means that there is no energy loss to the surroundings. Now, determine the change in temperature delta T of Q. Okay. Now, initially they're both at thermal equilibrium, but P is supplied with 24 kilojoules. So, for example, this is P and this is Q. This is your P, this is your Q. So we are supplying energy, 24 kilojoules of thermal energy. And what it will do is it will create a net transfer of heat until they both have the same temperature. So this is what we're actually talking about. So this means that 24 kilojoules, although it's supplied to P, but it's distributed in both P and Q. So this 24,000, the energy equals to mc delta T will be for P and mc delta T for Q. So this means that this 24,000, again, it's distributed in both of P and Q because they're in a thermal contact. So 0.54 times by 390. And one thing to remember, heat exchange is going on, but the temperature differences are going to be different because of the differences in their specific heat capacity. But what we know is that they're both starting at the same temperature. So they are both starting at the same temperature, they are both ending at the same temperature. So that's going to be the same. Plus 0.37 times by 910 times by delta T. Why? Again, they're starting at the same temperature, they're ending at the same temperature. So this means that this is delta T times by 0.54 times by 390 plus 0.37 times by 910 equals to 24,000. So delta T would be 24,000 divided by 0.54 times by 390 plus 0.37 times by 910. So we get, we convert this into normal form, we get 43.85 or roughly 44. Or 44 kelvins. 44. Nitrogen may be assumed to be an ideal gas. A fixed amount of nitrogen gas is contained at a constant pressure of this. Okay, one thing you need to remember. If it is an ideal gas, it obeys the PV over T equals to constant rule. This is the definition of the ideal gas, that its product of pressure and volume is directly proportional to thermodynamic temperature. So if this is an ideal gas, this means that this definitely obeys this relationship. Fixed amount of nitrogen gas is contained at a constant pressure. Variation of the volume V of the gas with temperature theta of the gas is shown. All right. So the temperature of the nitrogen gas is increased from 0 to 210 degrees. Determine the work done on the gas. So we know that this is happening at constant pressure. So the work done, change in work done, would be P delta V, since this is happening at constant pressure. However, yes, 1.6 10 raised to power 5. And now we need to determine what's the change in volume from 0 to 210. So I think this would be 10, 20, 30, 40, 50. Yes, okay, this is this. And this would be over here. So this is 0.8, I guess. Yeah, 2468. So 0.8 to 0.32. Sorry, this is 0.18 and this is 0.32. Okay, now this means that this is all we need to do. So 0.32 minus 0.18. So what we get, so 1.6 times by 10 raised to power 5 times by 0.32 minus 1.8. Sorry, 0.1, my bad. So 22,400 joules. However, this is expanding. This is expanding. As we can see, the gas is expanding. It's doing work. And the work is done by the gas. But we are trying to find out the work done on the gas. The key word over here is on the gas. If we were compressing, then that would be positive. But we are actually expanding. So this would be minus 22,400. We can actually convert this into two significant figures also. So minus 22,000 also. Since work done by gas is equal to 2400, work done on gas is going to be minus 22,400. So there are two differences, two different terminologies. Okay, now determine the number n of molecules of the nitrogen gas. So we can find this out. We have P, we have V, we have T. So we can use PV is equal to state equation, sorry, NKT. This is the state equation of the ideal gas. So N would be equal to PV over KT. So we know PV over T is basically constant because this is an ideal gas, but we still do not know. So we need at least one state known to us. One state known to us. So, and this T is not the Celsius, it is the thermodynamic temperature. So this is what you need to know. So pressure is 1.6, 10 raised to power 5. This is constant. Volume we can select somewhere. Let's say we select the 210 one, that was 0.32, divided by K is the Boltzmann constant, 1.38, 10 raised to power minus 23. This is given in the datasheet booklet, the form constant booklet, and temperature is 210 plus 273.15. So this would be 483.15. Right? Okay. So this we can do. So 1.6 times by 0.32 divided by 1.38 divided by 483.15 times by 10 raised to power 5 plus 23, we get 7.69 or 7.7, whatever we want to call it. So 7.7, 10 raised to power 24. If you use the 273, so the 1.5 will gone, so this would be just 7.68. Again, roughly rounds to 7.7. Okay, right. Okay. So the mass of a nitrogen molecule is this. Calculate the root mean square speed of the nitrogen molecule is this. Okay, so this has to do with the kinetic energy principle. That is 3 over 2 kT. And since we are finding the root mean square or mean square, this is going to be equal to half m mean squared speed. So basically the 2 and 2 get cancelled, so you can actually, so half m c squared equals to 3 by 2 kT. 2 and 2 get cancelled, so c squared would be equal to 3 kT over mass. So this would be equal to 3 times by 1.38, 10 raised to power minus 23, 483.15 divided by mass 4.7, 10 raised to power minus 26. Remember, this is going to be mean squared speed, not root mean squared speed. So 3 times by 1.38 times by 483.15, sorry, no, times by, and divided by 4.7, now the powers of 10, minus 23, plus 26, we get 425, this. So we can write it in the, oh no, wait, we don't need this actually, right? So we just need to square root this. We get 652 or 650 when we, sorry, CRMS is equal to the square root of mean squared speed. This would come out to be 650. Okay. Yeah. Moving on to question number 4. A small crystal is made to vibrate with simple harmonic motion. The variation with time t of the displacement x of one surface of crystal from its equilibrium position is shown. Show that the angular frequency of the vibration of the surface is this. So angular frequency is 2 pi over t, or 2 pi f. So if we are able to determine the time period, we can find that out. So time period, it appears to be 0.15 times by 10 raised to the power minus 6. So 2 pi 0.15 10 raised to power minus 6. So 2 pi divided by 0.15 times by 10 raised to power 6. So yeah, so if you convert this into the standard form, you get 4.188 or 4.2 10 raised to power 7 radians per second. Determine the maximum acceleration A naught of the vibration of the surface. So maximum acceleration will come from maximum displacement, right? So we just need the maximum acceleration. So we can actually just forego the minus sign. So maximum acceleration will come from maximum displacement. So maximum displacement is, we'll have to figure out. So 50 is distributed to between 10 grids, oh sorry, 10 small boxes. So this would mean 5 is each. So this is 40. So omega squared is 4.2 10 raised to power 7 whole squared times by 40 10 raised to power minus 6. So this would be 4.2 whole squared times by 40 times by, now the powers of 10, 7 times by 2 is 14 minus 6, we get 7.056, so roughly about 7.1, 10 raised to power 10 radians per second. Oh, sorry, no, meters per second. Squared, sorry. Okay, we have to write it over here. So 7.1, 10 raised to power 10. Okay. The crystal may be modeled as a single mass of 2.4 10 raised to power minus 4 kg that vibrates as shown in figure 4.1. Calculate the total energy E of vibration. So total energy, remember, it's equal to E of m omega squared x naught squared. So half mass is given as 2.4 10 raised to power minus 4 times by omega and x both squared. So omega we found out to be 4.2 10 raised to power 7 and the other one was 40 10 raised to power minus 6 whole squared. That's what we just have to do. So 0.5 times by 2.4 times by 10 raised to power minus 4 times by 4.2 times by 40 times by 10, because 7 minus 6 is just 10, and this is 338.6 or 7 you could say. So roughly 340 joules. Right. Okay. Moving on. The crystal generates ultrasound waves that are used to obtain diagnostic information about internal structures. The crystal is made from piezoelectric materials. Explain how the crystal is made to vibrate. So this is simple. All we need to say is that when we supply alternating potential difference across the crystal, it vibrates because of that, due to the piezoelectric effect. Yeah, that's what we just have to write. So an alternating potential difference is applied across the crystal which causes it to vibrate due to piezoelectric effect. That's it. Okay. A parallel beam of ultrasound waves is incident on a muscle bone boundary. Data for the muscle and bone bound are given in table 4.1. Calculate the percentage of the intensity of the ultrasound beam that is transmitted at this intensity. Okay, keyword over here is transmitted, not reflected. So we first have to find out the percentage reflected, and then from that we subtract and find out the transmitted. So be very, very, very careful about this. So first off, we need to find out the Z coefficients, the acoustic impedance values. So uh, Z is just equal to rho C or rho V, whatever you want to call it. So 1,100 times by 1,600, that is 1.76, 10 raised to power 6. And for this one, it's going to be 1,900 times by 4,100. So it's going to be 7.79, 10 raised to power 6. Okay. So so we first need to find out the intensity reflection coefficient. So that is, remember, it is Z2 minus Z1 over Z plus Z1 plus Z. So Z1 minus Z2 over Z1 plus Z2 whole squared. Actually, we should write this over here. So, right. So 7.79 minus 1.76 times by 10 raised to power 6 whole squared divided by 7.79 plus 1.76 10 raised to power 6 whole squared. Now if you notice how the indices work, the squared will actually distribute on this, and the 10 raised to power 6 squared also, and this would also be the square. So 10 raised to power squared, 10 raised to power 10 raised to power 6 squared, 10 raised to power 6 squared will get cancelled out, and we'll be left with just this. So square of 7.79 minus 1.76 whole squared divided by 7.79 plus 1.76 whole squared. Oh, my bad. So 3.98 or 0.39, you could say. So 0.3986 or 39%. So percentage transmitted would be 1 minus 0.3986 times by 100%. So 1 minus answer times by 100. So this is roughly about 60%. Okay, 60%. All right, moving on. A capacitor of capacitance C1 is connected in series with the second capacitor of C2. So this is C1, this is C2. Show that the combined capacitance C of the two capacitors is given by, okay, so again, this is a derivation, and once again, we do have derivations. Okay, so capacitance, net capacitance of capacitors in series, this is exactly what we need to show. So using the Kirchhoff's law, the combined potential difference would be the sum of potential differences across capacitors. Each potential difference is V is equal to Q over C. When we add them, it would look like this. Since they are in series, the current flowing through them would be the same. That means the charge flowing through them would be the same. So when we take out the Q and take it on the other side, V over Q, this would become 1 over C, basically. That's exactly what we just simply have to show. So neatly, let's write it. So since C1 and C2 are in series, so we can the charge flowing through them would be the same. Q1 equals to Q2. Let's say this is just Q. So according to the Kirchhoff's second law, you can actually write V over here. V would be V1 plus V2 equals to, again, Q is equal to CV, so V is equal to Q over C. So Q over C1 plus Q over C2, that means Q 1 over C1 plus 1 over C2. When you take Q1 the other side, V over Q, which is going to be 1 over C effective, or just that, 1 over C is going to be equal to 1 over C1 plus 1 over C2. So therefore, 1 over C is equal to 1 over C1 plus 1 over C2. Right, okay. Now, three identical capacitors, each of capacitance C, are connected in a network as shown. The variation of charge Q with potential difference V between the terminals X, Y is shown. Okay. Show that C is equal to this. Okay. So we have seen that C is equal to Q over V. This means that this is the gradient of this graph. So this is what we are going to write. C is equal to gradient of QV graph. So this is going to be the effective capacitance of the graph. So we have this C over here and this C over here, and this was the X and Y terminal. So all of these are C. So first off, we need an expression, and then we can equate it to the graph. So these two combined, the ones in the series, become C over 2, because in series it becomes 1 over C plus 1 over C equals to 1 over C effective. So this becomes 2 over C, and then when you take the reciprocal, this becomes this. Plus C coming from this one. So C over 2, C over 2 plus C equals to gradient of the graph. We need to figure out where the gradient is. So we look at the graph over here. Now we need the values for the gradient. So one value is this one, which is 6 volts and 400 microcoulombs, or just in this way, this is just coulombs. And this is 0 over 0. So that's what we just need, 6 and 400 micro. So 400 micro divided by 6 volts. C plus 1 over C is basically 3, 2, C equals to 400 at 10 raised to power minus 6 over 6. And C would be 2 times by 400 times by 10 raised to power minus 6 over 3 times by 6, 80. So 2 times by 400, 800 divided by 18 times by 10 raised to power minus 6. This would become 4, 4. This is 4.4, 10 raised to power 5 minus 5 farad. And this would be written as 44 microfarads. The capacitor network in figure 5.1 is changed and then connected to a resistor, is charged and then connected to a resistor of resistance 54 kilo ohms. The capacitor network discharges through the resistor. Okay. Determine the time constant T of the circuit. Okay, so first off, the effective capacitance is going to be 3 to C. So 44, 10 raised to power minus 6 times by 3 over 2. So times by 1.5. This comes out to be this 6.6 recurring 10 raised to power minus 5 farad. Now we need the time constant is equal to RC. So this is going to be 54,000 ohms times by 6.6 10 raised to power minus 5 farads. So times by 54,000 ohms, so we get 3.6 seconds. So 3.6 seconds. Right, okay. Determine the time taken for the discharge current to reduce to 15% of the initial discharge. So we need the discharge cycle equation. So I is equal to I naught e raised to power minus t over tau. So 15% means that the I over I naught would be 0.15. So 0.15 would be e raised to power minus t over tau. So when we do the ln on both sides, so we will have ln 0.15 minus t over tau. So t would be minus 3.6 times by ln 0.15. So minus 3.6 times by ln 0.15, and that gives us 6.829 seconds, so roughly just 6.8 seconds. Right, okay, moving on. Question number 6. An electric field and magnetic field are used to form a velocity selector. Charged particles called the ions pass into a region of uniform electric and magnetic fields that is between parallel plates as shown. Okay. The potential difference between the plates of the velocity selector is V. The separation of the plates is D and magnetic flux is B. Show that the speed U of the ions that pass undeviated through velocity selector is this. Okay, again, I'll just show you in the derivations. We'll also have that. So, this one, okay. So since the electric force will be equal to the magnetic force, electric force is equal to, as you can see over here, so QE is equal to BQE. E we know that is just V over D. So when we replace out the V over D over here, we can get to our required uh, form. So we go back. So QE equals to BQB. So QE QE will be equal to BQ. So we know that E is equal to V over D in the case of parallel plate. So when we replace our V over D equals to BV, we can then just rearrange to get our required form. So going back to the paper, and let's do this together. So first off, we need to show that the electric force equals to magnetic force in the case of velocity selector. So QE equals to BQ. U, they have already just given us everything, most of it. And E, sorry. Uh, so we have to write E is equal to electric field strength also. So Q and Q get cancelled, leaving us with just E, which is equal to V over D, equals to BU, which can now be rearranged as V over BD. That's it. That's all we actually just need to show. Positive ions with kinetic energy 4.1 10 raised to the power minus 17 joules and a mass of this pass undeviated through velocity selector when V is equal to 980 volts and D is equal to this. Okay. Determine B. Okay, all right. So we need to determine B now. So they have given us kinetic energy. That means almost with the kinetic energy and mass, we can find out the velocity. So first we need to actually do that. So we know kinetic energy is equal to half v squared. So let's write it as u instead. So u squared would be 2ek over m. So 2 times by 4.1 10 raised to power minus 17 over m, which is 3.2 10 raised to power minus 27. So u will be then equal to square root of this entire thing. So square root of 2 times by 4.1 divided by 3.2 times by 10 raised to power minus 17 plus 27. We get this 1.6. 10 raised to power 5 meters per second. And once we have that, we can just rearrange this equation to find out B. So B will be equal to V over du. So V is 980 divided by D is 3.6, 10 raised to power minus 2 times by U that we have already found, 1.6, 10 raised to power 5. So 980 divided by 3.6 divided by 1.6 times by 10 raised to power 2 minus 5. So 1.7 or 0.17 Tesla. That's it. Okay. A proton passes undeviated through the velocity selector. An alpha particle enters the velocity selector at the same speed as the proton. State how the expression in A predicts the alpha particle also passes undeviated through the velocity selector. So the expression was U is equal to B over, sorry, no, wait, V over, sorry, V over B, V over B, just to show you that, yeah, that was indeed the case, V over B. Okay, so as we can see this over here, that for this expression, for this relationship, for the velocity selector, it is indifferent and does not care about the mass or the size of the charge. So it only cares about how much potential difference is across the parallel plates, how much strong the magnetic field is, and how much separation of the parallel plates is. So uh, the the expression is independent of size of mass or magnitude of mass. Actually, we should write magnitudes of charge and mass. Right. By reference to figure 6.1 and to the forces acting on a positive ion, determine the direction of the magnetic field. Okay. So we go back over here. Then these are the path of ions. Now, the electric force is acting downwards. That means that the magnetic force has to be upwards. So if electric force is downward, since we're talking about electric force being equal to magnetic force, this will only happen if they're, in opposite directions. So, right, okay. And this is the direction of the ions. Now, we are talking about force acting on a positive ion. So positive ion, when we consider the Fleming's left-hand rule, the path of ions, positive ions, so current is over here, magnetic force is upwards. So this means that the index finger, which is the field direction, is into the page. So this is all we just have to write and explain. So we can say is that the electric force acts downwards. So magnetic force will be directed upwards to balance the forces. Using the left-hand rule, using Fleming's left-hand rule, it can be determined that considering current is towards right, force is upwards, then magnetic field direction will be into the page. That's it. You can even write this over here. So force over here, current in this, and then the B over here. All of these are perpendicular to each other. Right, okay. The positive ions in B enter the velocity selector with greater kinetic energy. On figure 6.1, sketch the path of these ions. Okay, so greater kinetic energy means greater speed. Greater speed, what does greater speed mean over here? So greater speed would mean that the BQU would be higher than QE. Then that means that the force, magnetic force, would be greater than E. So we already said that magnetic force is directed upwards, so the general resultant force direction BQU minus QE would be greater than 0. That means upwards. So that means the direction of resultant force would be upwards. So it's going to go this way. That's it. That was the reason. Okay, all right. State Faraday's law of electromagnetic induction. So just to show you this. Sorry, my bad. Ah, as you can see, a very frequently examined question. It states that when magnetic flux passing through a coil changes, electromotive force is induced in the coil, magnitude of which is proportional to the rate of change of magnetic flux. This is also over here. Sorry, again, my bad. Yeah. Electromotive force is induced in the coil, the magnitude of which is proportional to the rate of change of magnetic flux. So that's all we have to do. It states that when magnetic flux passing through a coil or a conductor changes and EMF is induced, the magnitude of which is proportional to rate of change of flux. Magnetic flux. Right. Okay. A metal rod is accelerated uniformly from rest in a uniform magnetic field. Okay. The rod has length L and flux density of the magnetic field is B. An electromotive force EMF is induced in the rod. A variation with time t of the induced EMF is shown. Explain how a 7.2 shows that E is proportional to the V of the rod, or velocity of the rod. So we can make two connections over here. So they have told us that this is being accelerated uniformly from rest. So acceleration uniform means that the rate of change of velocity, uh, or dv over dt is constant. And here in the graph, we can see that the change in E over change in time, or the change in E over change in time, that is also constant. So this must mean that the E is directly proportional to the velocity. That's all we have to show. Since rod is accelerating uniformly, velocity is increasing at a uniform rate. E is also increasing uniformly as seen from constant gradient, uniform gradient. Therefore, it shows velocity is proportional to E, induced EMF. All right. Use Faraday's law to show that the variation of E with time t is given by this. Okay. Right. So we know that E is equal to rate of change of flux with time, which is basically V A over change in time, or just simply time, just for simplicity we can say. The area that it is covering, is given by this length, and the distance it covers per unit second. So let's call it B L times by, oh sorry, wait, did they give us L? Rod has length L, okay. S over T. Now, if we notice over here, S over T is V. So it can be written as BLV. So finally, we have E is equal to BLV. Actually, we should have written all of this on the left side because it's part of the working. So on the left side over here. Okay. Right. Now, since this is accelerating, we have u plus at. U is 0 because it started from 0. So v is equal to at. So therefore, it will become b L at. That's it, simple. The length of the rod is 0.45 meters. The acceleration of the rod is this. Determine the value of B. Okay, so this means that we first need something over here. So wait a second. The length of the rod is this. The acceleration of the rod is this. And determine the value of B. Okay, all right. So we have E is equal to BLAT. So if we take T on the other side, we will have change in E over change in T is equal to BLA. So delta E over delta T will come from the graph. 0.3, 2 and 0.3 millivolts. So 0.3 10 raised to the power minus 3 divided by 2 equals to, B would be delta E over delta T divided by LA. So L is 0.45, acceleration is 7.8. So, right. Now we just simply need to write it here. So 0.3 divided by 2 divided by 0.45 divided by 7.8 divided by 1000. So we get 4.27 10 raised to the power minus 5 Tesla. So we can round it to 4.3 10 raised to the power minus 5 Tesla. Right, okay, moving on. State what is meant by a photon. So photon is a quantum of electromagnetic energy. Simple. Quantum of energy, quantum of electromagnetic energy. So let me show you over here. Fundamental particle of electromagnetic radiation with zero mass, zero electric charge, which carries energy and momentum. But the better definition is discrete packet or quantum of energy of electromagnetic radiation. It is a discrete packet or quantum of energy of electromagnetic radiation. Right, okay. A laser emits a red light of single wavelength. The light is produced when electrons move from higher energy levels to lower energy level. The difference in energy between the two levels is this. So basically they are talking about de-excitation. So when electrons jump from higher level to lower level, a photon is released. So we need to figure out which one is that. So this is, for example, E1. This is our E2. So difference, they've already given us this. So the difference in energy levels is equal to hc over lambda. So they've already given us that. However, to find out the wavelength, we need to convert this electron volts into joules. Otherwise, we can't do that. So lambda is equal to hc over delta E. So h is the Planck's constant, 6.63, 10 raised to power minus 34, speed of light, 3.0, 10 raised to power 8, energy, 1.96, 1.6, 10 raised to power minus 19, to convert it into joules. Now 6.63 times by 3 divided by 1.96 divided by 1.6 times by 10 raised to power minus 34 plus 8 plus 19. So we get, we need this in meters? Yes, we need this in meters. So 6.342 or 6.3, 10 raised to power minus 7. The power of the beam emitted by the laser is 10 raised to power minus 2 watt. Calculate the number of photons emitted per unit time by the laser. Okay, power is simply energy per unit time. Energy is N times by H C over lambda over time. So we need the N over T over here, right? So HC over lambda, we already know. This is this 1.6, 1.96 electron volts they have given, and we just need to convert this into joules for that. So that will give us that. So power is equal to N over T times by the change in energy. So the N over T will be equal to the power over change in energy. So power is given as 1.0 10 raised to power minus 2 divided by change in energy is 1.96 10 raised to power, 1.96 times by 1.6 10 raised to power minus 19. So we get 1 divided by 1.96 divided by 1.6 times by 10 raised to power minus 2 plus 90. So we get 3.188 or 3.2 10 raised to power 60 per second. The photons are incident normally on a surface. Half the number of photons are absorbed by the surface, half are reflected. Determine the average force exerted by the beam of photons on the surface. Okay, now we know by the definition of force, force is the rate of change of momentum. And P over here is P equals to NH over lambda, because we're talking about some number of photons over here. So this may not be the N that's represented over here, but since we have half and half, so we'll deal with that. So change in momentum for absorbed photons, it will be P divided by 2, because you have, so it's, for those photons, it's just P back, but since you have total number of photons, let's say we connected N with, N with a total number of that, so we can write it just P over 2, which is going to be, in short, NH over 2 lambda. Then for reflected, it's going to be 2P over 2. Again, half because it's a half number of reflected. And this is going to be the change in momentum 2P. So this is just P, which is just going to be NH over lambda. Now, P over 2 plus P just simply becomes 3P over 2. So force is net change in momentum over change in time. So it's P over 2 plus P over change in time, which leads us to 3 by 2 P over change in time. Let's see how that works out for us. So 3 over 2 P is NH over lambda and divided by T. Right. So in 1 second, or in particular amount of time, which we now know to be per second. So we can employ that. So 3 by 2 times by 3.2 times by 10 raised to power 16, Planck's constant, 6.63, 10 raised to power minus 34, divided by the wavelength that we have figured out. So wavelength was 6.3, 10 raised to power minus 7. Right, and that's about it. So we have 3 divided by 2 times by 3.2 times by 6.63 divided by 6.3 times by 10 raised to power 16 minus 34 plus 7, and we are getting 5.0 something, 10 raised to power minus 11. So this is the average force. So we can write it as 5.0, 10 raised to power minus 11. Right, okay. So just to show you recap, this P and this P are important. So for absorbed, you have U over here, but V is 0. So it's just V minus U, or just M U, basically. But for this one, if this is U, this is V, the change in momentum would be M V minus minus U, which is just going to be 2M. If both are the same, basically, so this will be just 2M. So this is the reason for doing 2P and P, basically. All right, moving on. Polonium is an unstable nuclide. A nucleus of polonium-193 decays to a nucleus of lead by emitting an alpha particle. Radioactive decay is both random and spontaneous. State what is meant by random and spontaneous. And then we have half-life. Okay. Random and spontaneous is something that comes very frequently, and as you can see this over here, we will show you where did it go? Okay. State what is meant by radio. Okay, right now, sorry. As you can see, so many years written by. So this means that these two are very frequently examined. So random means that the decay of radioactive nucleus cannot be predicted. Each decay event is entirely independent and occurs with a certain probability over a given time nucleus. So basically, we cannot predict when a certain radioactive nucleus will decay. Spontaneous, on the other hand, means that the rate of decay is not affected by physical factors or environmental factors. So random means that the decay of a nucleus cannot be predicted. Each decay is independent with a fixed probability of decay in a time interval. This independent keyword over here, this is the probabilistic events that is being independent. Spontaneous means that the rate of decay is not affected by any external factor. That's it. Half-life. It is the time required for activity to decay to half of its original value. We do know activity is directly proportional to the number of nuclei also, so that is better. Okay. Data for binding energy per nucleon of particles involved in the decay of a nucleus, polonium-193, are given. Determine the energy EV released when a nucleus of polonium decays into a nucleus of lead-189. So first off, we just need to, quickly write the equation. So we have polonium decays into lead and alpha, right? So we know that, right? So we need it in, okay, so we already have that. Okay, so this is given binding energy per nucleon. We need binding energy in total. So 7.774 times by 193, 7.826 times by 189, 7.074 times by 4. Now, the binding energy released in total or just simply energy released would be energy or binding energy of products minus the parent. So 7.826 times by 189 plus 7.074 times by 4 minus 7.774 times by 193. So we get 7.826 times by 189 plus 7.074 times by 4 minus 7.774 times by 193. So we get 7.028 or 7.03. We can also write electron volts. Okay. A pure sample of polonium-193 contains N0 nuclei. After a time t of the sample contains N nuclei of polonium-193. The variation of ln n over N0 is shown with T as shown. Okay. State the name of quantity that is represented by the magnitude of the gradient of the line. Okay. So what we can actually do over here, if you forget that, n is equal to n0 e raised to power minus lambda t. And this is also written in the formula, definitions and formula. So this, let me point out this thing. All right. So going back, if we take n0 on the other side, we are left with e raised to power minus lambda t. When we take ln on both sides, we get ln n over n0 is equal to minus lambda t. So this is sort of y equals to mx, m being the gradient. Right, okay. State the name of the quantity represented by the magnitude of the gradient. So lambda is the radioactive decay constant. So radioactive decay constant. Use figure 9.1 to determine the half-life in milliseconds of polonium-193. So how is radioactive decay constant related to that? So half-life is related to by that ln2 over lambda, again also written over here. Right. Now, all we have to do is to figure out what the gradient is. So first off, we need to figure out the gradient. So the gradient lambda is equal to negative lambda is equal to the gradient. So that will be equal to, let's figure this out, 0, 0, and the other one, let's choose this one. This one is good. Okay. By the way, this, you see over here, 0.6. Okay. So 0.6 and minus 1. All right. So you have, so again, minus 1, minus 0, 0.6, minus 0. And not to forget that this was in milliseconds. So the time was in milliseconds. So, minus 1 divided by 0.6 times by 1000. So we get minus 5000, since we need to retain a little bit of accuracy before we put this in. So ln2 over 5000 divided by 3. So ln2 divided by 5000, times by 3, we get this value. So 4.15 times by 10 raised to the power minus 4 seconds. We need to convert this into milliseconds. So how we can actually do that? It's a simple math procedure. So for example, if you have 10 raised to the power minus 4, and we need to make this one minus 3 instead. So we multiply by 10 and divide by 10 over here. So the right side becomes 10 raised to the power minus 3. This becomes 0.415. So this is it, basically. So 0.415, 0.42 milliseconds. That's it. All right. Positron emission tomography PET scanning uses a radioactive tracer. State what happened to the positrons emitted by the tracer. Again, this will be answered in the frequently examined questions part also. So the tracer, so what happens with the tracer? So basically it collides. Oh, right. Okay. So whatever this is, yeah. So basically what's happening over here is that positron encounters the electrons in the body, undergoing annihilation, releasing 2 gamma rays in the process, which is then further used for energy. The other question was, explain why a tracer with approximately half-life of approximately 2 hours is a suitable tracer to use. This is a very question that comes up. So let's see if we can find this. There was something. Right, okay, right. This one. So just why 110 minutes or 2 hours is suitable half-life for a nuclide used as a tracer. Long enough to conduct diagnostic imaging after the tracer is administered, but short enough to limit prolonged radiation exposure to the patient. So that's it, basically. So let's answer both of these one by one. So positrons emitted collide with electrons causing annihilation, resulting in energy release in form of gamma photons. Right. Okay. And then it is long enough for diagnostic imaging process, but short enough to not cause prolonged radiation exposure to the patient. That's it. All right, moving on. State what is meant by luminosity of the star. Again, we can answer that over here. Luminosity is the total energy emitted by the star per unit time. It is you can also say it is total power of the radiation. Also, total energy emitted by a star. Emitted by a star per unit time. Right. Explain how standard candles are used to determine the distance to a galaxy. Okay. So basically what happens is that standard candles, whatever form they are, we have studied about two types of standard candles. So what we do over here, we standard candles have known luminosities. So if we know the luminosity of a standard candle in a particular galaxy, we can find out or approximate the distance to that using the known luminosity and the flux density or flux intensity, sorry, that's coming to our Earth. So on Earth, it's flux intensity. On the star or the standard candle, it's luminosity. So whatever energy that's reaching us, we use that to approximate the distance. And again, once again, this is also answered over here. Explain how standard candle or distant galaxy can be used to measure this. Standard candle luminosity is known by measuring its observed radiant flux intensity. Applying the inverse square law, distance d to the galaxy can be estimated. Right. So a standard candle's luminosity is known by measuring its observed flux intensity and applying the inverse square law. You can actually flux intensity F, luminosity L, the distance D can be estimated. Although this is fine, but if you want to write the formula also by F is equal to L over 4 pi d squared. That's it. The sun rotates on its axis. Points X, Y, and Z are on the equator of the sun. As shown, the wavelengths of the light from points X and Y are observed and recorded in the table. Observed wavelength from X, observed wavelength from Y. Okay. Sun rotates with a period of this. Show that the radius of the sun is, oh wait, sorry, it's a period of this. Show that the radius of the sun is this. Right, okay. So what we need to find the radius of the sun. First off, let's list the quantities that we have. So from the period, we can find out omega 2 pi over t. And have they given us something? Oh, okay, all right. So v, we know the speed is r omega, so that is 2 pi r over t. Have they given us the radius? They haven't. Okay, they haven't, but oh, show that the radius of the sun. Okay, okay. So this is basically going to come up. Okay, my bad, I forgot. Right, and we don't know the v over here, but we need to figure out v using the Doppler effect or the redshift formula. So y doesn't appear to move. So y doesn't appear to move because it's at the center. So we can use this as the lambda, the original lambda. But since it is the wavelength at x is slightly lower, we can see the redshift over here. So we can use that as a difference of wavelengths. So what we can do, v over c is equal to change in wavelength over wavelength. So we have 656, 283, 1 minus 656, 2877. Oh wait, sorry, what? Oh my bad, sorry, it's the other way around. Because it's redshift, sorry, my bad. So 2877, 656, 2831. Since it is in nanometers, you can do that, but the thing is, the 10 raised to the power minus 9 will get cancelled over here. So 656, 2831. Also 10 raised to the power minus 9. So V will be equal to 656, 2877 minus 656.2831 divided by 656.2831. This is this value. V over C is equal to 7.009 10 raised to the power minus 6. So V will be equal to 7.009 10 raised to the power minus 6 times by speed of light 3 10 raised to the power 8. 3 10 raised to the power 8, and this comes out to be 2.103 10 raised to the power 3 meters per second. And now we are going to use this in this. So R would be T V over 2 pi. Period is 2.07 10 raised to the power 6. Velocity is 2.103 10 raised to the power 3 divided by 2 pi, and just hope I'm not missing out anything. Okay, so this times by 2.07 times by 10 raised to the power 6 divided by 2 pi, we get this. So 6.93, 6.93, 10 raised to power 8 meters. That's it. Now, state and explain how the expected wavelength of the light observed from Z compares with the emitted wavelength. All right. So, wait, sorry, what? Yeah, right, okay. So, emitted wavelength is the same for all of them because, and will be approximately equal to the wavelength at Y. But since this is going into the page and this is coming out of the page, like for example, the direction of rotation over here. So this is the point where the red shift will appear to happen, and this is the point where blue shift, that means reduction in the wavelength, will appear to happen. So Z is moving towards the observer. Therefore, observed wavelength will be less than, emitted wavelength. Right, okay. The luminosity of the sun is 3.8 10 raised to power 26 watts. Use the information in V1 to calculate the surface temperature of the sun. Okay. So over here, we will use the Stefan-Boltzmann law. So Stefan-Boltzmann over here, 4 pi r squared sigma t raised to power 4. For sigma, we'll have to see the data sheet. So Stefan-Boltzmann law. Why we don't have to go through anything else, because we know the radius, we know the surface temperature. Oh no, sorry, we need to find the surface temperature. What else? We know the luminosity. Right. So Stefan Boltzmann law. L is equal to 4 pi r squared sigma t raised to power 4. So we need to find out the surface temperature. So T raised to power 4 would be L over 4 pi r squared sigma. So luminosity is 3.8 10 raised to power 26 divided by 4 pi. The radius, do we have radius? Yes, sorry, yes, we actually found 6.93 10 raised to power 8 squared times by Stefan Boltzmann constant. So Stefan Boltzmann constant is 5.67 10 raised to power minus 8. Right, 5.67 10 raised to power minus 8. This will be t raised to power 4, so we will have to figure that out. So, 3.8 divided by 4 pi divided by 6.93 squared divided by 5.67 times by 10 raised to power 26 minus 16 plus 8, we get this. So 1.110 10 raised to power 15. So T will be T raised to power 4, 1 over 4. So what we need to do further is answer raised to the power 0.25. So we will get 5.7 10 raised to power 3. So 1 to 5,772. So basically, you can say 5,800 if we round it to two significant figures. So 5, 7, 7, 2.7 Kelvin would be exact. Right. And that's the end of the paper. All right. So again, feel free to reach out to us. Do check out the Patreon link that we will give out in the description. As you can see, your preparation will be helped with the grade booster pack. As you have already seen that there are so many questions that we have already uh, seen in the grade booster packs, many definitions, many formulae, many key points. And if you feel that I made a mistake somewhere, or if you would like some additional explanation on some part, do reach out, tag the time and or the question part, and then ask your confusion and question. And if you feel that you still would like some more one-on-one consultation, feel free to reach out to any of the WhatsApp, email, or any text media given in the link tree, and I'll be happy to help you out. Meanwhile, take care. See you in the next video. Bye bye.